Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to finally have a chance to take a look at what solids look like on a molecular level. So one of the big things to note about solids is that because we have all of these atoms in a very tightly packed network, they tend to have very common and consistent and repeating arrangements. Now, they can get a little messy, as we'll talk about later, but a surprising number of solids do tend to keep these nice regular patterns. And it's one of the reasons why you have such cool geological formations with nice flat surfaces, is because they essentially cleave along this nice crystalline lattice. So even though it might not seem so, you can often use these crystalline structures to describe a lot of different species. So keeping that in mind, what we can do is when we look at a solid that has this regular repeating pattern, we say it has a crystal structure. What we do is we look at this whole big mess and we go ahead and we find one repeating unit that essentially, if I take that unit, which is going to exist on the lattice cell, I'm going to take that repeating unit and I'm going to call it a unit cell. So I can then take this unit cell and replicate it along the lattice by repeating it in every direction. So as I go to the left, right, up, down, no matter which way I go, I should be able to see that same repeating pattern. And we can actually describe more solids than you'd think as an infinite number of these repeating unit cells. And in fact, this is often usually how we describe things like geology, metallurgy, and it can even be used in a lot more biological systems than you'd think. And by looking at these crystal structures, we can tell a lot about the property of a system. We're going to go ahead and start today by looking at some of the more common crystal structures. So ones where the repeating unit forms a nice square. So these are called cubic structures. So the simplest of these unit cells is called a simple cubic cell. So you can see the reason why it's a cube because, well, it's a cube. And it's simple because all we have is one atom at every single corner. Now, this actually doesn't occur that commonly when we're looking at elemental species. Only really good example of this is going to be polonium. However, what we can do is use it to describe a lot of different ionic and molecular species, where you can have a lot of different species where you can have maybe one molecule occurring at every vertex, or where you have this as the base structure and something consistently fills in the middle. But as a result, it's a very good place to start, especially because it's fairly easy to describe. It's a simple unit cell, which we can think about like a six-sided die, where I've got one atom at every corner, and it's going to be surrounded by six nearest neighbors, one up, one down, one to the right, one to the left, one back, one forward. So one in each of the given directions. If you want a good example of this, go ahead and stack some die, and you'll notice that it will have six neighboring die. Now, the next thing we need to do is figure out, on average, how many atoms are going to be in one of these unit cells. So your natural instinct would be to say, ha, there's 8, count them, 1, 2, 3, 4, 5, 6, 7, 8. But here's the problem, is when we go ahead and show it as this nice stacked set of balls, we have to remember that the cube that we're repeating only contains 1/8 of each of these spheres. And you can kind of see this in this diagram to the lower left. So we've got 8 different corners, each of which contains 1/8 of an atom. So if we multiply these together, it means that we have one atom. So there's one whole atom per unit cell. And if we go ahead and repeat this, you can kind of see how we end up generating it. So some people will prefer to go ahead and move the lattice, and you'll find one atom at the center, and then it's repeated in every direction. But for convenience sake, we're putting an atom at every given corner. And so when we have, then we can go ahead and try and describe the dimensions and the occupancy, so is actually the structure of the system, by realizing that I can find the volume, because I know that each side has a length of twice the radius. I have one radius going from the center of the atom to the middle of the side, where this atom then meets up with its nearest identical neighbor, which has another distance of 1 radii. So each side has a distance of 1 radii. And then we can figure out the volume by taking, well, using our basic geometry, the cube of each side. So length times height times width. But since they're all the same, this means all I need to do is take that length and raise it to the 3rd power. And since the length is twice the radii, this gives me a total volume of 8 times the radius cubed. So ta-da! We can determine exactly the exact size of a simple cubic cell by just knowing how big my atom is. So if you can go, and there's plenty of resources where you can go ahead and look up the radii of different atoms. So simply by knowing the radii, we can find the volume of an individual unit cell. And then if I know how many atoms are present, so for example, you could use the mass to determine the moles to determine number of molecules, or atoms in this case, and number of atoms times the volume per atom to get the total volume of the sample. So you can actually determine a lot of cool properties using this simple relationship. However, one of the things that we're often very concerned about is, well, how much of that volume in this unit cell is actually atom and how much of it is empty space? Because if I want to put a lot of atoms in a closed space, which is the whole point of having a solid, I'm going to want to maximize that number. I want as much of it to be atom and as little of it to be empty space as possible. So what we can do is determine the volume of each of the individual atoms. So we have 1 atom per unit cell, and that atom has a volume of 4/3 pi r cubed. So this is again from basic geometry. So then I can find the percent of the volume that's my atom and the percent that's empty space. So I'll take the volume of my 1 atom and divide it by the volume of my cube. So when I do this, well, a lot of messy numbers, but it turns out it simplifies down to pi over 6. R's cancel, 4 divided by 3 gives us 2 on the bottom. 4/3 over 8 gives us 6 on the bottom, and it just becomes pi 6. So it turns out the ratio is about 0.52, or 52% of this lattice is atom and 48% of it is empty space. That's not exactly great, because what it means is if I went ahead and I put this simple cubic cell under a lot of pressure, it's probably going to go ahead and try and deform to make something else, something more tightly packed. And it turns out one of the easiest ways we can go ahead and try and raise the occupancy is by taking my simple cubic cell and putting an extra atom in there. So one of the simplest places you could put that atom is in the middle of the cell. You have this big empty space in a simple cubic cell. So what you can do is place an atom in the center, and you go from SCC to BCC. I apologize, there's going to be a lot of acronyms. So this is body-centered cubic, because I still have a cubic cell. Every cubic cell has 1 atom at every corner. But when I have body-centered, I add an extra atom to the middle, to the body. And unlike the simple cubic cell, it turns out that the body-centered is commonly used by a lot of different elements. So if you're looking at iron, sodium, potassium, and tungsten, all of these tend to possess this unit cell. And things like iron and tungsten are really important as they're often used in a lot of metallurgical processes. Iron is, well, iron. And it turns out whenever you want a very heat-resistant substance, you tend to use tungsten as an incredibly high heat capacity and is very useful in a lot of high heat applications. So what we can do is then try and figure out exactly how many neighbors each one of these atoms has. And remember, in the case of the simple cubic cell, it was 6. But here, we can start by looking at that central atom. And you'll notice that it touches 4 different atoms above and 4 different atoms below. So we have this central atom is adjacent to 8 other atoms, 1 in every diagonal direction. So this gives us 8 nearest neighbors. So it's connected to a lot more atoms than we had for the simple cubic cell. And you'll note that this will form a fairly nice set of structures. Now, the next bit is trying to figure out, did we actually increase the occupancy? Will this be a more dense solid? Will it have more atoms per the same amount of volume? So the first thing we need to do is figure out how many atoms are in this body-centered cubic. So we still are going to have one atom in the corners because we have 8 corners with 1/8 of an atom each, but now we've added one extra whole atom in the center. So this means that we have net, on average, 2 atoms per unit cell. So the next thing we need to do is figure out, well, how big is the cell? So this one gets a little bit more complex on the geometry, so go ahead and take my word for it. What we can do is figure out the length of each side. So this is going to be a lot of Pythagoras, but we know the length when we go from one corner to the other. This is going to be essentially 4 times the radius. 1 radius to get to the central atom, 2 radii to get across, and 1 radii to get to the other corner. So now we need to relate this central corner, C, to each of the sides. What we know is we can find, using Pythagoras, we know that a squared times b squared plus b squared gives me c squared. So I can use this to find that central diagonal. So we know that this length should be essentially twice a squared. Then we can do the same thing to get c by using this diagonal and the length of the base of the sphere. So we know that the b here is twice a squared, and we have an a squared here. So we add them all up and we get 3a squared. So we know that this angle is going to be, the square of c is going to be equal to 3a squared. So if I solve for a, it's going to be equal to 4 times the radii divided by square root of 3. So math is a little bit complicated, but don't worry about that. Just take it on faith. So each side has a length of 4r over the square root of 3. Then what we can do is cube that to go ahead and determine the total volume. So this gives us a very messy number. And then what we can do is use this for a lot of different properties. So one of the coolest ones we can do is density, because we know the volume per atom, but we can also use this to figure out the mass of atoms per unit cell. And remember, this unit cell has 2 atoms. So the mass inside this unit cell is going to be twice the mass of each atom. Note that this is going to be the mass per atom and not the mass per mole. If you need to convert this, you can go ahead and use our good old friend Avogadro's. So in order to determine the density, we can take the total mass over the total volume, and ta-da, you can calculate the density. It's a very common practice when you're trying to figure out the properties from just a unit cell alone. However, practically, we're also interested in, did we actually increase the occupancy? So what we can then do is, similar to before, we find the volume of atoms in the cell. So now it's going to be twice the volume of the atom being examined, because we have 2 atoms per unit cell. And then we're going to divide it by the volume of the unit cell. So again, the math gets really messy, but it turns out we can simplify it to pi times the square root of 3 over 8, which turns out to be about 68%. Note that this is 12% greater than the simple cubic cell. So this is a much more efficient way to end up packing materials together. And it gives us a lot of big advantages. And it's the reason why the simple cubic cell is so rarely occurring as its own in nature, but the body-centered is actually quite common. But not quite as common as the next cell we're talking about, which is the face-centered cubic cell. So in this case, we start again with that simple cubic cell, but instead of putting 1 atom in the middle, I put 1 atom at every given face, thus face-centered, 1 atom every face. So this one actually occurs, again, for a lot of different materials, including copper, silver, gold, so our coinage metals, and lead. So if you ever wondered why lead was often painted and acted as a substitute for gold, part of the reason why is they have the same unit cell. So they're going to have a lot of the same properties, even if they occur in different places on the periodic table. So the first thing we want to go ahead and figure out is how tightly connected any one of these atoms is to its neighbors. So we can do this by looking at the nearest neighbors. So this one's actually a little trickier. So one of the big things I want you to remember is that Again, the atom here at the top of the unit cell is essentially going to be identical to the one in the equivalent position at the bottom. These two, pretty much identical. So you'll note that we're going to have 4 neighbors in the plane. So that's these white balls. But we're also going to have 4 neighbors touching below. So 1, 2, 3, and 1 in the back. So I've got 4 below, 4 in the same plane, but if I've got 4 below, it means I also have 4 above. Take this atom, look up. So we're going to have 12 nearest neighbors, 4 below, 4 in the same plane, 4 above. It's going to be a little tricky to get the hang of, but give it some good practice. So you'll note that we went from 6 nearest neighbors in the simple cubic to 8 nearest neighbors in the body centered to now 12 nearest neighbors in the face centered. So we have a lot more contact with a lot more atoms, which is going to make this, not surprisingly, in general, more stable. However, we also care about things like density and occupancy. And for that, I need to know the volume of the system. And that means I also need to figure out how many atoms are per unit cell. So this one's a little bit trickier. So again, we're going to have 1 atom in the corners, but we're also going to have 6 different sides, 1 in each of those given directions. But that means I've got 6 atoms on the faces. However, that whole atom isn't inside my unit cell. Only half of it is. So if you look at this cross section, half of it is in this unit cell, half of it is in the neighboring. So each one of them only counts as half. So 6 times half gives me 3. So that gives me a net of 3 atoms on the faces, 1 in the corner, for a total of 4 atoms per unit cell. So we can also do a similar set of math to figure out the length of every side based on the radii. So again, we're going to be using Pythagoras and the fact that if I go from this corner to this corner, it's going to be 4 times the radii because every atom has to touch the other. So 1 radii to get to the central, 2 radii to get across, and 1 radii for the final bit. So doing this, we can find out that every side has a length of the square root of 8 times the radii. So using this, I can then calculate the volume of the unit cell by just taking that number cubed, which gives me a much nicer number than for the body centered. But I can use this to then determine the density. Now note, instead of having 1 mass, twice mass, I now have 4 atoms. So it's 4 times the mass of that atom divided by this volume. So you will need to know the mass of the atom and its weight and its size. So using that, I can then calculate the percent occupancy. So I know the volume of every individual atom, 4/3 pi r cubed. I know how many atoms I have. It's 4. And I know the total volume per unit cell. So I can then take these numbers, simplify the math, get a kind of messy equation, but it turns out that this is going to be about a 74% occupancy. So note that this is 22% greater than the simple cubic, which is immensely more tightly packed and slightly more tightly packed than the body centered, 6%. So this means that if you can adopt the face centered cubic, you often do. However, due to the arrangements of electrons, some atoms and molecules are forced to occupy the more convenient body centered. So we start to see a lot more tight competition. And it turns out these 3 simple unit cells describe a lot of simple crystal structures and are quite convenient. And a lot of more complicated systems can be approximated by just taking the structure and modifying it a little. So next time we're going to be looking at a few little bit more complicated structures. However, I promise we are done with the messy geometry. Until then, take care.